So the first thing we need to do is be a little clear about what we're asking for when we ask for an equilibrium. If I want an equilibrium, what am I looking for? What's the definition of an equilibrium?
Is it a place where b sub t plus 1 minus b sub t is equal to 0?
So yeah, when we were saying we were after equilibrium, or equilibria if you're plural, we wanted a value where if you started at that value, it would never change. Once you get to that value, it just stays the same from there on. That's what we sort of mean by equilibrium. If you're riding your bike down the road, you are at an equilibrium because you just keep going down the road. You don't, even if somebody knocks you a little bit or a wind comes by, you stay in that nice upright position and you don't change. It doesn't change easily off of that position. It stays there, it stays going that direction. So we're looking for values so that if you plugged it in for b sub t plus 1 would just be exactly the same value again, and b sub t plus 2 would be exactly the same value after that, and you would just stay on that value forever. So we're not looking, if you look back at the approach most of you were taking originally, you knew that we had looked for where the thing was 0. By the way, this is my attempt to get you out of student think, okay? Get you to actually think about the mathematics you're doing and not do the student think thing. You have been well trained, unfortunately, in math classes that what you do is the teacher gets up and does 3 or 4 examples of something, and then you go off and you do 30 examples of exactly the same thing. The names have been changed to protect the guilty, but you do essentially the same thing following essentially the same steps. It's a sophisticated form of mimicry, which on my less pleasant days I call monkey see, monkey do. So you knew that we took the right-hand side and we set it equal to 0, and that's what we had done last time, and so that's what we went about doing. But what you were actually finding then were what values of b sub t lead to b sub t plus 1 being equal to 0. So we figured out that, oh hey, if you plug a 5 in for b sub t, you get a 0 out for b sub t plus 1. But that means that your value of b sub t did what as you went from t to t plus 1?
Could have gone up or down.
Well, it started at 5. And the next one was 0. Is that an equilibrium? No, we changed. We went from 5 to 0, which is the opposite of an equilibrium. An equilibrium you don't change. Here we were finding something that automatically did change. So you want to step back from these problems and think through the definitions. How does it apply to the situation? One of the nice things about applied mathematics, when you're really using math to do something in the real world, is that almost never is it a completely clear cut. This looks exactly like this, and so I can just do exactly the same thing over again. Now, after some thought, you frequently get it down to this is really the same as this, and I can do the same thing again. But rarely is it just clear cut where you can cut and paste, like you usually do in a math lesson. So instead, I don't want b sub t plus 1 to be 0. If things are not going to change, what do I want to be 0? The difference between b sub t plus 1 and b sub t. So that when I took that step, that time step, nothing changed. So what I'm really interested in when I look for an equilibrium is b sub t plus 1 minus b sub t, and I know that if I'm going to be in equilibrium, I want that to be 0. I want there to be no change between consecutive values. So, what do I need to do over here?
Subtract b sub t.
I subtracted b sub t over here from this side of the equation, so in order for it to be legitimate, I have to do it over here. So we would have now 5 b sub t, because I subtracted 1 off of there. And now I am interested in when this expression right here is actually equal to 0. Now, that's not the only way to do it. We talked about how if we found the derivative of this expression, that would be giving us the rate of change of b sub t. And if that were 0, that would be what we wanted. We wanted the rate of change to be 0. So we could go take the derivative of this, set the derivative equal to 0, solve for that, and that would be a different way of finding our equilibrium. The other really nice thing about applied mathematics is that there's almost never only one way to do it. There's usually several, and some of them there's usually some really fun, ingenious ways of getting around things that makes it fun to do the math.
With b sub t plus 1 equal like another x value, you plug it in. So usually we do derivatives like y equals the terms of x.
Yeah.
How does that work with kind of having like 1x and an x on the other side? It's a different x, but it's still an x value.
So, if we came down here, so we would end up with this kind of thing showing up. Let's see, sorry, that explanation isn't going to go very well. Let me try this one, which is a little more heuristic, but b sub t and b sub t plus 1 are actually measuring the same thing, like you say. So you have sort of an x equals x kind of thing going on there. So really what I have here are two expressions for, in essence, the same quantity that I'm measuring. Whatever b sub t is measuring, this is just two different ways of sort of figuring it out. So if I find the way it changes over here, so the rate of change, if I figure the rate of change over here and I figure the rate of change over here, they're both the rate of change of the same thing. And so they both, in essence, give me the same information. I don't know if that clarifies it. If you get into the details of it, you can go back to calculus and you take these expressions, but instead of a plus 1, you put a little delta t here. And then you can go through and do the whole, actually, a full derivative derivation out of it, where you divide both sides by delta t, and you take limits, and you do all of that kind of stuff, and we could work through all of that, but I don't think that would be profitable at the moment, so. Right. This method down here is more in the spirit of the fact that this is a discrete situation. It's not continuous. We're not allowed to let our times go to 0. And so we're not allowed to take, and the b sub t's are discrete. Those physically can't be allowed to go to 0. You can't take differences and allow them to go to 0. So realistically, this is what works in terms of actually matching what's happening in reality. The derivative idea is a nice mathematical idea which actually works. You can use it. But if you look at how the mathematics is working, it's actually violating a lot of things that are true about the real situation. If these are bison, then we can't take the limit as the number of, the amount of the bison that we're looking at goes to 0. It's a strange sort of concept to think of sort of the bison
You start
disappearing.
cutting them in half.
Yeah, well, that's sort of a gross way of thinking. I thought more of the disappearing is, I see the head, that's the eyeball. Anyway. So this way down here fits the reality perfectly, matches what we were doing last time, but just understand there are other ways to approach it, and they work, and that's fine. Okay. So now we would go find the roots of this, and those would be our true equilibrium points, and it's you. So there's one at about negative 2.07, one at 1.847, one at 5.22, and we put those up and figure out where it's positive and negative and do everything like we did it over here, just with this expression instead of the original Questions about how that works? The other thing, this is a math class, and so we occasionally will get integer answers, but in the real world, if it comes in as an integer, you guess somebody cheated. You should at least have some random errors showing up. So even if you're counting bison when you do the math, you have these little random errors showing up. But, all right. Questions about equilibria or solving simple difference equations? Yes?
So after you found those equilibrium points, what do you do to find whether those are stable or unstable?
Unstable. So here we have is 5.22, this is 1.847, this is negative 2.07. So then we go back to our expression down here, and again we're interested in how things change. That's what we're after. So we're interested in this expression right here. And if you look at that, if you sort of think of it, the b sub t plus 1 minus the b sub t as being your y, b sub t as being your x. So we're just changing the names, but it can help you think a little better about it. If I were to graph that, I know that it has a root over here at about negative 2, 1 over here, and 1 over here. Those are my three equilibrium points. And since this has a positive number in front of the x cubed, I know that it has a shape that way, or you could go plug in a point or two just to figure out where it's negative and where it's positive. So I know that the value is negative if I'm less than the negative 2, it's positive in between negative 2 and 2, it's negative between 2 and 5, and it's positive past 5. So if I come over here, I know that I get positive values here, negative there, positive there, and negative there. Does that make sense? And if I look at the y value that I'm finding here, so here the y's are negative, there they're positive, there they're negative, there they're positive. The y value is the change in b sub t. So I know that down here the b sub t's are changing in a negative direction. So if my starting value is below this equilibrium here, then since b sub t plus 1 minus b sub t is negative, I know that b sub t plus 1 is going to be down, more negative, and that it's just going to keep doing that. It's just going to get more and more and more negative as time goes on. In between here, I know if I start at a value here, that I change in a positive direction. And so I am going to go up and get close to this equilibrium. I know that if I ever hit an equilibrium, I just stop. So here I'm just going to get closer and closer to that equilibrium. Here, if I start, I'm going to change in a negative direction, so I'm going to come down, get close to this equilibrium. If I start up here, I know I change in a positive direction, so I'm just going to head up. Questions about that analysis? We have some frowning faces, so ask your question.